Bacteria is everywhere. What you are looking at is a mix of good bacteria and bad bacteria. These are good bacteria, like the lactobacillus that helps digest your food, while these are bad bacteria, such as cholera or tetanus, which enter your system and expose their toxins to make you sick. We call this group pathogenic bacteria. Our traditional methods of fighting these bacteria were born from Alexander Fleming's discovery of a bacteria-killing mold called penicillium, which led to modern-day antibiotics. So, how it works today is that you get sick because one of these guys embeds itself in your body and releases toxins into your cells. You take these pills, and then bam, all better, right? Wrong. Unfortunately, it can get complicated. Complicating factor number 1, not all bacteria are bad. Remember those two populations of good bacteria? Well, to be a little more specific, one is a neutral bacteria. It does no harm to your body, but nor does it contribute in any way to your inner workings. But the other is what we call an essential bacteria, like the flora that live in your intestines. The symbiotic, or mutually beneficial relationship we share with these bacteria significantly impacts our body's metabolism and weight homeostasis. The problem is, most antibiotics don't discriminate between these guys and these guys. You pop that pill, and bam, everybody's gone, and you're left with no one to help you digest your food properly. Complicating factor number 2, DNA randomly mutates. It does so in your cells, and it does so in plants, and it does so in bacteria. Some of these mutations don't really affect how the bacteria functions, while others have the annoying effect of giving rise to antibiotic resistance, which is when bacteria acquire the ability to survive exposure to an antibiotic, like this little guy here. In fact, for many of the antibiotics that we've deployed since the 1930s, we've observed resistance to those antibiotics. So how do we get around these complicating factors? Thankfully, there's people like this lady working on solutions to overcome these problems. Dr. Fiona Brinkman is a microbial geneticist at Vancouver's Simon Fraser University, and she is at the forefront of the battle against bacterial pathogens. Dr. Brinkman and her team of scientists are working to develop an alternative means of combating bacterial pathogens called an anti-infective. But before we get into how an anti-infective works, there's an important concept that we big, important scientists use that we'll need to get you up to date on. And that is the concept of selective pressures. Without getting too deep into the genetic nitty-gritty of selective pressures, let's say Tim and I are going to go for a hike on Grouse Mountain. We're sitting in the car, air conditioning blasting, and are both comfortable. All things considered, we are both equally well adapted to this environment. We reach Grouse right around noon. Tim, in his blue baseball cap, is not bothered by the sun and keeps a pretty steady pace, whereas I, being the savvy traveler that I am, have forgotten to bring a hat and am quickly getting tired in the midday sun. At this point, the sun's heat is acting as a selective pressure, and Tim is better adapted. Now, fast forward to the evening. We're making our way back down Grouse, the sun has gone down, and Tim is a little chilly and is slowing his pace some, whereas I brought a sweater and am trotting happily down the path. Now the selective pressure is the cold, and I am the better adapted one. Now, let's take this concept and apply it to bacteria. A population of pathogenic bacteria have entered your system. You get sick and you take antibiotics. All things being even, if every member of the population is equally susceptible to the drug, you'll wipe out the pathogen and then recover from the bacterial infection. But what if one member of the population is resistant to the antibiotic? Once you've wiped out the antibiotic-susceptible portion of the population, you're left with this one guy who can't be killed with the drugs we know and who now has free reign over the warm, wet, nutrient-rich environment that is your body. So now, instead of a treatable population of bacteria making you sick, you've got a resistant strain that can proliferate inside your body. In this case, the antibiotic is acting as a very strong selective pressure in an environment where resistant strains will thrive. But what if we just disarm the pathogens of their weapons, or toxins? If you can disarm pathogenic bacteria instead of killing them, you're still keeping them from making you sick, but without killing them and, more importantly, without killing their competition and therefore selecting for resistance. Well, this is great. Sign me up. Unfortunately, it's not as simple as that. Disarming bacteria means that we need to find their toxins, the proteins that make them so harmful. Unlike broad-spectrum antibiotics, This method is meant to target proteins that are only in pathogens and are not seen in good bacteria, and it takes a very long time even just to identify these proteins, let alone develop drugs that target them. But thanks to Fiona and researchers like her, we're getting there. With at least one anti-infective compound having already gone through clinical trials, it may yet be some time before anti-infectives become available behind the counter, but in the meantime, rest assured, whether it's sooner or later, new and improved weapons for combating bacterial pathogens are on the way.